Okay, it's 2 now. Let's get started. So hello everyone, welcome to Ask Seminar series. This is John, the seminar coordinator. So I will be moderating the seminar with Kathy, our communication manager, and a couple of housekeeping things before we get started. So this seminar is being recorded, and we will post the recording on our YouTube channel. And we will have the Q&A after the presentation. So please feel free to bring up any questions you may have. If you don't have a mic, we usually encourage you to speak up, but if you don't have a mic, you can chat other questions and we'll read them out. Usually our director will be joining us, but today he is on travel. So unfortunately, he won't be here. And before we get started, I will hand the ball to Kathy to introduce the speaker. So Kathy, please go ahead.
Thanks, John. So I'm happy to introduce our seminar speaker today, Dr. Greg Hakim. Greg is a leading atmospheric scientist currently using deep learning models for novel research on predictability, data assimilation, sensitivity analysis, and extreme events in current and historical time periods. He is the author of over 100 scientific papers and 2 textbooks on weather and dynamic meteorology. Greg has previously chaired the advisory panel for the mesoscale and microscale meteorology division at the National Center for Atmospheric Research and served on the advisory committee to the Geosciences Division at NSF and the President's Advisory Committee on University Relations. He has undergrad degrees in math and atmospheric sciences, a PhD in atmospheric science from the University of Albany, State University of New York. So I'm just going to go ahead and hand it off to Greg to please give us this talk. Thank you.
Thank you, Kazi. Thank you, John. Thank you all for coming. It's a pleasure to be here. So the topic of today's talk is about using new tools. It's an old technique, but with these new tools of fully differentiable weather models, we have access to new science that we didn't have before. So the outline here for what I'm going to talk about is these new opportunities, primarily from machine learning models, but they're creeping into traditional models as well. And those two facts are computational efficiency and gradient facilities that we've historically called adjoint models. And after a brief review of that, I'll talk about 2 applications. The first is to use these techniques to test the 2-week limit of atmospheric predictability. This has been the limit that's been around for, or thought to be around for about 50 or 60 years. We're going to do this by computing shadowing trajectories, and it's essentially very long window 40 var, if you're familiar with those ideas. The second application is going to be gray swans, and these are plausible, you might think of them as near miss extreme events. They haven't happened, but they could. And we're going to use deep gradient descent to explore the possibility of these events occurring near observed events in the recent past. So I think we're all familiar now with this deep learning revolution that has affected our field, the rapid emergence of machine learning weather models in the early part of this decade rapidly led to forecast skill that was near or better than operational models almost overnight. And they were doing this with dramatically lower computational cost. Moreover, we're getting basically a free ride on the deep learning revolution, which is started with the large language models and other generative approaches for images. And this has brought a lot of new participants into our field and given us access to new tools and techniques, such as automatic differentiation, which is used for training these models, and it's also being used now for refactoring traditional models. It's also brought in a lot of people from the private sector competing in a space that was previously occupied only by folks mainly in big government labs. So the timeline on this Cambrian explosion was quite rapid. Like I said, in the late 20-teens, around 2020, there was a steady increase in skill on the y-axis. The red line here shows you forecast skill relative to ECMWF's IFS. And then the banner year in 2022, where Huawei's Bangu weather model first exceeded the performance of the IFS. And then there was a rapid proliferation of models from other large private companies, and also now from government agencies, including NOAA and ECMWF. So these new opportunities with these models, as I mentioned, is computational efficiency. The obvious thing is they allow us to have much larger ensembles that we've had in the past, but also, I think less well explored is the possibility for a larger scope of hypothesis testing as a way to find hypotheses worth testing with the expense of more traditional models. So it's a way of prospecting in a high dimensional space of hypotheses. The second opportunity comes from this automatic differentiation, which is basically the chain rule of calculus made super easy. These are adjoints of the forecast model used for backpropagation, and this is useful for sensitivity analysis, data assimilation, and hypothesis testing. So adjoint models have had a long history. There's this famous review article by Ron Errico in 1997 in the Bulletin of the AMS. At that point, he was summarizing a decade of work that went back to the 1980s on the development of these adjoint models and their application to the topics that I just mentioned. So what's new with these machine learning models? Well, the models are very, very structurally simple. They're just chained layers of a nonlinear operator on a linear map, ax plus b, where this nonlinear operator g is a known function that's smooth and has as many derivatives as you like to take of it. So these machine learning frameworks are exploiting this efficiency to compute gradients both in the forward and backward direction. Now, from my point of view, this is a massive change from the old adjoints described in Errico's review paper, which are still used, by the way, at operational centers. So in ECMWF, they're still using traditional adjoints. They have tangent linear models, but the new ML models don't have code for these models. They don't have tangent linear models, and they don't have inner loops. So there's no tangent linear inner loop wrapped in an outer loop of the nonlinear forward paths, which is much more expensive. And from my point of view, this is a real game changer. So let's move on to the first application, which is testing the 2-week limit of atmospheric predictability. So the most predictable scales are, in fact, the energy containing scales. This is the Nystrom and Gauge power spectrum for various quantities derived from aircraft data. The wind or the kinetic energy has this steep slope at large scale. So long waves are on the left, planetary scales, and you can see on a log scale, there's much, much more power at these large scales than there is at the mesoscales. And the slope changes from -3 at the synoptic and planetary scales down to this -5/3 on the meso and convective scales. And that, in fact, is the crux of the predictability limit. So one view of the limit of predictability is linear. It derives from small errors in initial conditions and error growth rates that are set by the leading Lyapunov exponent. And typically, this is diagnosed using perfect twin experiments where the model is perfect and small defects in initial conditions are introduced. And then the rate at which trajectories diverge is measured, and that gives you the leading Lyapunov exponent over long periods of time. So this shows you on the left, the Pangu weather model does this beautifully. And on the right, neural GCM, which is a hybrid model, which I'll be using extensively in this talk, both do very similar things. The errors grow in the temperature field at a nearly perfect exponential rate with a doubling time of about 21 hours for Pangu weather, about 24 hours for neural GCM. This is close to conventional traditional models. The blue line shows if you cut the error in the initial conditions, you get the same growth rate and you just extend the time of predictability out accordingly. So provided we can decrease the error in the initial conditions, this point of view, which is valid on the large scales, synoptic and planetary scales, the -3 spectrum, is semi-infinite predictability. Now, the real limit, as we understand it today, comes from the -5/3 spectrum, and this is fully nonlinear. So this involves a scale-dependent error growth. Although I'm not going to get into the details of the theory, it only formally applies for isotropic eddies. That is, eddies that have the same scale in every dimension, which means for the troposphere, they've got to be less than about 10 kilometers. And there's no question about the validity of this theory in a -5/3 spectrum exclusively. It's been validated extensively with numerical experiments with the Navier-Stokes equations. Now, the rub is that when we apply this to weather, This is a numerical extrapolation to larger scales using our traditional weather models. Up until recently, that's all we had. So this is a speculative extension of the theory that requires an interaction between the meso and convective scales and the large scales, and that requires a model. And so Palmer et al. Called this the real butterfly effect as an absolute finite time predictability barrier and a breakdown of the continuous dependence on initial conditions for the solution. So this has been, again, tested many times over in a bunch of papers with different groups. This is one from Sells et al. Showing that if you take the spread in an ensemble and you shrink it as a way of mimicking the reduction in error, so the x-axis shows how much smaller the error is getting, and on the y-axis is some limit of the time where skill is lost. That's the predictability limit. And you can see from the operational limit right now of around 10 or 11 days, as the error is shrunk in the initial condition, the lead time grows up to this limit. And so we get here to 99.9% error reduction. We're basically hitting a wall that we cannot get past. And this is thought to be due to this rapid error growth due to cloud processes, convection, and latent heating. Well, we do have new models now to test these ideas. These machine learning models, which are completely data-driven or hybrid models, they don't resolve small scales at all. There's no mesoscale in most of these models, all the ones that I'll be using today. So there's no thunderstorms. They don't need to generate or integrate over these processes, so they don't have an accumulation of error from small scales either. They simply take us over a large time interval without necessitating an integration of differential equations with closure schemes at small scales and unresolved processes. There's no need for any of that. And so that gives us a different view on the dynamics. So these shadowing trajectories that we're going to use to test the predictability limit are generated as follows. So we have some initial condition with some assumed error, and we make a forward pass forecast. So this is going to be ERA 5. We make a forecast with a model, and we accumulate a loss function. And that loss is going to be the squared difference between our forecast and a reference. And the reference for us is going to be ERA 5. So this is a measure of how close our forecast is to ERA 5. And of course, as we get long lead times, the error grows, and that dominates this loss. Then using the gradient facilities that come with the frameworks for these models, we're going to compute the gradient and back propagate it to the initial condition, where we'll take a small step in the direction that is predicted to lead to less error with respect to ERA 5. And then we repeat this process as many times as we like, typically hundreds to thousands of times, compared to order 5 to 10, which is all that we can afford to do with the traditional coded adjoint models of traditional physics models. So our first application was to the Pacific Northwest heat wave in 2021. This was led by Major Trent Vonich, who's visiting the University of Washington on a fellowship to get his PhD with me at the University of Washington. This heat wave hit us hard locally. It was also one of the top 6 global extremes of the last 50 to 60 years. Importantly, it's not in the training data for GraphCast, which is the model we're going to use for that shadowing trajectory calculation I just talked about. Derivatives are going to come from the JAX framework, and as I said, the initial conditions and the verification come from ERA 5. So here's a quick snapshot of the results. So in the upper left, you see ERA 5 at the peak of the heat wave in the 500 hectopascal heights in the black lines, and the 2-meter air temperature anomalies from the June climatology are shown in the colors, with anomalies greater than 25 degrees Celsius in yellow. So we have a big ridge, and we have extraordinarily hot temperatures. In the upper right, you see a control forecast that was initialized 10 days earlier with ERA 5. So this is just GraphCast making a forecast, and it's not very good. It actually puts a trough right in the region where we have the big ridge in reality. The lower left shows you the result of this shadowing optimization, where we go back and we try and find better initial conditions 10 days earlier that improve the forecast at this time. And so what you can see is we have about a 90% error reduction, both the heights and the 2 meter air temperatures are nearly perfect. So we found small changes to the initial condition that give us a nearly perfect 10-day forecast. So our initial assumption was that this was mostly model error that we were encoding in the initial conditions. So we put these initial conditions into Pangu weather, which is another model. It has a different neural network. It has different input variables, different time resolution, different spatial resolution. They're both trained to emulate ERA 5, but they are in fact different models. And you can see the fact that there's different resolution here just by the pixelation of the 2 meter air temperature field. Once again, ERA 5 verification in the upper left. The Pangu weather control forecast is in the upper right, also not very good. Using the GraphCast optimized initial condition as a Pangu weather input, we get, again, a nearly perfect forecast. So this says to us that there's really something in these initial conditions that leads to better forecasts. In the lower right, you see a rather severe truncation of those initial conditions to T60. So basically, we're throwing away everything except for the coarse scales, synoptic and planetary. We're removing all the small scale information, and we still get most of the improvements. So this leads me to have some optimism that these are potentially realizable improvements. We're not talking about very small scale tweaks to initial conditions that might be difficult to resolve with observations and data assimilation systems. Okay, well, maybe we got lucky. So we decided to test this on a much larger sample size. So Trent he tweaked the algorithm a bit, which I don't have time to get into. And he ran it twice a day for all of 2020, which results in a sample size of 732. And so here's the results. In terms of the loss, as a function of lead time on the x-axis, so the y-axis is forecast error, essentially. The gray lines show you the controls. So these are forecasts for every day, initialized with GraphCast ERA 5, and it shows you the growth of error over forecast lead time. So the error grows exponentially and then saturates at around 10 days to 2 weeks. The green curve shows you the result of this optimization. And not only can we optimize some of the forecasts, we can optimize all of them. And in fact, on average, the improvement is pretty similar to what we saw for the heat wave case. At 10 days, it's about an 86% reduction in forecast error. Now you'll notice that the error starts to grow again at around 2 weeks. And that's because the optimization ends there. There's a float 32 precision limit where the step we need to resolve to go downhill in the algorithm is no longer resolved at float 32. But when Trent took this to float 64, the process goes out further. So we get skill improvements out past 30 days. And we're left with this slope with an error doubling time of about 6 days. That's much slower than the 1 day doubling that we saw for twins and that we're seeing here for the controls. But so there's some other source of error that's contributing to the drift of these forecasts that is irreducible in the framework that we've got right here. I don't have time to get into this today, but it looks like this is model error that we're seeing, and that's a subject of our current research. So to conclude this portion of the talk, if the atmosphere were intrinsically limited by small-scale error growth, we shouldn't be able to do this. So this is not a way or a recipe to improve real forecasts, operational forecasts. It's an existence proof. We're showing that there are initial conditions that lead to forecasts with this model and another one that we've tested, neural GCM, that go out much further, more than twice as long as we previously thought to be possible. Okay, so transitioning on to application number 2. This is relatively recent research applying these gradient facilities to extreme events, and in particular, using initial condition sensitivity to discover near-miss events, gray swans. So I like to call this gray swan factory because we're manufacturing them, and it's a delightful activity. I'm having a lot of fun basically exploring what's possible. It's really great for what-if testing. So this is with Aishwarya Agarwal. She's a high school student at a local school here near Seattle. And she was helping me out on this project. So these gray swans that we're going to manufacture are extreme events that are plausible, but thought to be unlikely. This compares with black swans, where the probability is so low that we don't know about these events until they happen. So the gray swans are a bit like storylines, if you're familiar with that. And like I said, you can think of these as potential near miss extreme events. So the hypothesis we're testing here is that we can manufacture these events using directed gradient descent. And we can generate samples for training machine learning models, for example. So we have a very limited time period over which to train models. And how can you train on a once in 1,000 year event or a once in a 10,000 year event if it hasn't been observed? Well, you can manufacture it with this technique, and you can make as many of them as you like, actually. So this might be potentially very useful for training models. So the experiments I'm going to show you involve taking ordinary Atlantic hurricanes. These are real observed hurricanes, and looking for nearby analogs similar to Hurricane Sandy in 2012, which took this left turn hook into the mid-Atlantic coastline. So the method we're going to use here is this nonlinear gradient descent. We're going to use neural GCM, and the reason for that is that it's basically a traditional physics model. So it has a dynamical core that's integrated in spherical harmonics, vorticity, divergence, temperature anomalies, 3 variables for water species. And the main difference is it takes all the parameterizations for everything else and wraps them into a single learned closure, which is then trained on ERA5 data. So for this Gray Swan factory, we have a paper up on arXiv if you're curious about that, and I'll show you some of the highlights here. So Hurricane Sandy, I imagine many of you are familiar with this storm. It was a devastating storm. This is a bizarre surface map for those of you that are synoptically inclined. We have both a hurricane symbol and frontal symbols on the same map with the same storm. So it was a hurricane that took this bizarre left turn hook and brought very high winds and severe flooding along the coast. This is the tidal gauge at the Battery in New York Harbor, and at the time that exceeded the previous record high by 4 feet. And it disfigured much of the New Jersey coastline, including Mantoloking here, where the barrier island was breached. Well, applying neural GCM to Sandy and making a 3-day forecast using ERA5 initial conditions produces actually a really good forecast. So what you're seeing in the red lines here is the geopotential height at 1,000 hectopascals. So here's the storm right on the coast. And then in the gray contours, you're seeing the 500 hectopascal geopotential heights with a few selected contours. So if I trace those out for you, you can see we have a classic omega block where Hurricane Sandy is the left flank of the block. And so one of the questions is this downstream block essential to the Sandy-like outcome, basically preventing the storm from the hurricane from doing a typical offshore recurvature and encouraging this left turn? So here's the track of Sandy. It was taking what appeared to be a typical recurvature out across the North Atlantic. And as you may remember, a lot of the forecasts early on were taking it that way. And then some of the forecasts started tapping into the possibility of this left turn, which is in fact what happened. And the pressure was extraordinarily low. It got down at its minimum to 940 hectopascals. Please remember that value for what I'm about to show you. The storm we're going to first test this on is Hurricane Fiona, which is a hurricane that took a similar track in 2022. It was a moderately intense hurricane that became extratropical close to the Canadian Maritimes and moved up across the western North Atlantic up toward Greenland. The question we're asking here is, can we encourage this storm by making small changes to the initial conditions at this time right here, the 22nd of September, 2022, to do a Sandy-like left hook? And so we're going to construct a loss function to try and encourage that to happen. And we're going to focus on the 1,000 hectopascal heights at a grid point very close to where Sandy made landfall. So here is the objective function that we're using. It has three components. The first one is what I just mentioned. So G represents the geopotential height, and we have a target value which is set below what we think is achievable. And so we have a positive value that we can search for in the optimization process. So we're going to try and drop the pressure at that point, which incidentally is nowhere near where the storm actually tracked, right? So the storm was way up here in Nova Scotia, and we're trying to encourage it to go along the mid-Atlantic coastline. We have two penalty functions. The first one is on the size of the perturbations to the initial conditions, which is ERA 5. So we're going to encourage those to be small. We're going to stay close to ERA 5. And the other one is a regularization penalty on the tendency, the first model step. Otherwise, we get an accumulation of noise in the initial condition, and this discourages that noise. So the optimization process proceeds as follows. This is a single step through the loop. Given an initial condition, and our very starting initial condition is ERA 5, we make a nonlinear forecast with neural GCM, and we compute this loss, this J. We then use the automatic differentiation facilities to backpropagate that loss to the initial condition using JAX. And we compute an increment to the initial conditions that is predicted to make a smaller value of J. So that's why we have a minus sign here. We use optax to manage this with the atom optimization routine. And then we simply go back to step one. With that modified initial condition, we do another forward nonlinear pass. So again, the difference here from the classic approach is there's no tangent linear model in code. It's all just neural network. And there's no inner loop. We're not going to have a tangent linear inner loop followed by a nonlinear outer loop. It's simply nonlinear outer loop, backpropagation, repeat the process. So this is what the loss function looks like as a function of epoch. So the optimization starts on the left, and this is 10 iterations, 100, 1,000. So the loss function is slowly decreasing. And then at around 50 to 100 epochs, we start to get this much faster descent. And then it slows down to something that looks a bit like a power law, and then continues to drop. The contribution is coming mainly from the loss on the final state. That's the thing we're trying to optimize, drop the geopotential height along the mid-Atlantic coastline. And the penalty functions are also, there's a linear ramp on the initial condition penalty, and then it's finding initial conditions that are even closer to ERA 5 that also are achieving the objective. And the initial tendency is becoming smoother. So we're getting, apparently, in the loss what we are trying to do. So let me show you what happens in the optimization procedure in these fields that I showed you before. So 1,000 hectopascal heights in the red lines, 500 hectopascal heights in the black lines. So this is ERA 5, the starting initial conditions at the 22nd of September at 00 UTC. So here's the hurricane, just east of the Bahamas. And the key player here is this mid-latitude trough, which is going to move to the east in the jet stream and pick up Fiona and drag it up over the Canadian Maritimes. So here's the control forecast. 2 days later, the forecast for Fiona. This is a very good forecast. This is pretty much best track. It goes right up over the Canadian Maritimes. The upper level trough has amplified. So I'll go back. You can just see here's the trough. It's moved to the east. And as I said, it's picked up Fiona. We have a nice tilted structure there, and a baroclinic development is underway. So we're going to try and adjust this now to lower the pressure, lower the 1,000 hectopascal heights right here where my cursor is. All right. Same solution, now 20 epochs into the optimization. So I'll go back. This is the control. And by doing this back and forth 20 times, we've changed the solution a little bit. I'm going to go forward. Here's 40, 60, 80. So right now, this is the part of the optimization where the loss started to fall really fast. And if you look at the gradient in the geopotential height field, you could see that's right when the gradient is passing over the optimization location. It's repositioning the storm. So now I've skipped ahead to 200 epochs and then 400, 1,000. So we now have a storm exactly where we went to place it. And in terms of mean sea level pressure, it has an intensity that's over 20 hectopascals lower than Hurricane Sandy. So as you just saw, this gray swan solution is a smooth function of this gradient descent. Those first 50 to 100 epochs are changes to the initial condition that lead to a forecast that repositions the storm on the coast. And then after that, since it's in the right place, it's making adjustments to the initial conditions that mainly affect the intensity and lead to a storm at the end that's stronger than Hurricane Sandy. So what I'm going to do now is with this gray swan, after 1,000 epochs, I'm going to show you the time evolution of the optimized solution, the gray swan. Same fields. On the left is the control for comparison, and there's the blue dot. That's the target optimization point. This magenta line shows you the hurricane center best track, and I'm going to put a little X for the particular time that corresponds to the forecast. So this is the 6-hour forecast. So you just look visually, they look very similar. You can see that the storm is a little stronger in the gray swan. That's perhaps not a surprise. There are subtle changes to the trough at 500 hectopascals. If you have a keen eye, you'll see there's a little more troughiness here to the west. This is the 24-hour forecast. So again, relative to best track, that control forecast is bang on. The trough now is noticeably deeper. If you use this darker contour as a reference point, you could see the upstream trough is stronger. Its phase is a little bit further west, and we're getting a stronger interaction now with a stronger hurricane. This is the 36-hour forecast, and now the difference is becoming pretty dramatic. We're getting a very strong interaction with the classic westward tilt with height between the surface low and the upper level trough. Both are deepening rapidly, and we're getting essentially a vortex alignment and a vortex capture, so that 12 hours later, we get this incredibly intense storm in the same place as Hurricane Sandy, a radically different solution from the control. So what do these perturbations look like? So in terms of the 500 hectopascal height fields, you can see them here in the black contours. So that shows you the gray swan initial condition, and the magenta contours show you ERA 5. So these are not teeny tiny perturbations. They're finite amplitude. In fact, you can see the difference field on the right is on the order of about 10, 20, 30 meters in geopotential height. You can see that this difference field is shifting some of the features in the mid-latitude flow, and it's changing the intensity of these features. Now, the reason why I have the color fill in both of these is this experiment shows you if you limit the modifications to the tropical cyclone domain, that's the left side here, and below you see the forecast that results from that. So this is only allowing the gray swan perturbations near the hurricane. And you get this forecast. It's in fact very similar to the control. It's a little bit slower. And on the right, you have the complement to this. This is changes to the environment everywhere except the tropical cyclone. And that gives us something that's very close to the full solution. So because these are both fully nonlinear solutions, the sum of these two doesn't add up to the gray swan, but in fact, it's actually not that far off. It's a leading order approximation. So this suggests to me that most of what's happening here is not so much the intensity of the hurricane, but it's changes to the mid-latitude flow that lead to the interaction with the hurricane. Okay, what if we were to do really big ensemble, but that's perturbed randomly? ERA 5 with random perturbations that are conditioned to have the same amplitude as the gray swan statistically. So you get this range of outcomes. So everywhere you see a dot, This is a forecast for the same time as the control in the gray swan, and the intensity in 1,000 hectopascal heights is shown down below. So none of these 1,000 ensemble members do anything that's anywhere close to the gray swan, which is here along the coast and an intensity that's off the color chart. Most of the uncertainty with random perturbations leads to a long track uncertainty, and there's a bit of a cross track uncertainty. Most of these perturbations lead to weaker storms rather than stronger storms. So massive ensembles are not going to find these solutions. They require these targeted, deep, directed nonlinear optimizations. Okay, was this peculiar to Fiona? Am I just cherry picking here? So I just went through and just eyeballed a bunch of storms over the last decade that had similar tracks to this offshore Western Atlantic to see if we could convert them into gray swans. So here's Hurricane Lee from 2023. On the left, we have the control forecast starting from ERA 5. On the right, after 1,000 epochs of this gray swan optimization procedure that I've talked about. So it's not a particularly notable event in the control, but it certainly is for the gray swan. Once again, we get a very sandy looking storm, but the large scales around it don't look like sandy. We don't have a big omega block. We, of course, have a ridge because there's a very deep trough here. How about another one? Here's Umberto in 2019. In this case, Umberto also got picked up by a trough and redirected offshore. Here's the gray swan. Small changes to the initial condition lead to a Sandy-like outcome. And again, the large-scale flow is quite different from Sandy. Maria, 2017. Again, another offshore event in the control and a very Sandy-like outcome, but with plenty of differences relative to Sandy in the gray swan. I think you get the idea. This can be done pretty much to any storm that takes a track like this. This is Gonzalo in 2014. So every storm I've tried this on, I get a sandy gray swan. The initial condition perturbations, using the format I showed you before. So the black contours are the ERA 5, 500 hectopascal geopotential heights, and then the magenta lines are the gray swan, optimized initial condition at the same time. And then the color fill with the reference legend on the right here is the difference in those. So, some of these perturbations they're pretty big. You could see it. In other cases, they're not so big. So for Umberto, for whatever reason, they were smaller. And if you look carefully, you could see interesting things happening here. So for Maria, for example, repositioning the tropical cyclone was a very important thing. So shifting it to the south was more important. For Lee, shifting it to the southwest. And in other cases like Gonzalo, it didn't matter too much. And what was much more important was changing the strength of upstream troughs and other aspects of the extratropical circulation. There's a lot of fascinating dynamical questions that could be asked here about how these evolutions are so close to what actually happened and lead to such radically different outcomes. All right, to summarize, leave plenty of time for questions. I've showed you how to use gradient sensitivity over really long windows of time so that we're not just linearizing around short time periods like we traditionally do with adjoint or ensemble-based sensitivity. And we applied that to, in the first case, testing the limits of predictability. And what we found is that making small corrections to reanalysis initial conditions leads to very large reductions in forecast error at 10 days and, in fact, skill beyond 30 days. So again, I want to emphasize that this is an existence proof. We're showing that there are initial conditions that are, in fact, quite close to ERA 5 that produce accurate forecasts. This is not a recipe for how to find these in real time. That is an active area of research by us and others. The second application is to these extreme events, gray swans, like Hurricane Sandy. And what we've found is that such events are lurking disturbingly closely to ordinary storms. And what's especially disturbing is these near-miss storms have an intensity lower or with greater intensity than we have previously observed in the historical record, in the instrumental record. And again, I want to emphasize this is an existence proof. It is certainly not a probability assignment on this outcome, but it is a demonstration that with this model, these initial conditions lead to those outcomes. So this might be potentially useful for what-if testing, and as I mentioned earlier, to generating training data for machine learning models where you don't have to rely on observing events that didn't occur over the relatively short period of time that we've had observations. So that's the story. Thank you very much, and I'm happy to take questions.
Thanks, Greg. So if you have any questions, please raise your hand. I will call on you. You should all be able to unmute yourself.
Oh, Louis, good to see you on here. Mike Evans, my goodness.
Good seeing you again, but I was a little bit late, so I'm not going to ask any questions. I didn't get the
Okay.
first 15 minutes.
Thanks, Louis.
I have a question, if I might, Greg.
Go ahead, Mike.
Hey, Mike.
Hi, this is really neat work. Could you say a bit more about how the gradient ascent works, the automated approach that kind of gets around this tangent linear approximation? I'm just very curious about how you go back that far without an adjoint just blowing up.
Right. So there are definitely memory management issues that I've had to learn how to use JAX checkpoints and things like that. So this is kind of in the weeds, but in a nutshell, how this works is forward forecast, and then JAX archives enough information so that when it goes backwards, it goes back through the neural network. It goes back through the dynamical core too. So the solver, the ODE solver, is also written in JAX, so it's fully differentiable. And so it goes back through one time step, which is 1 hour in this model, and it just keeps going all the way using the chain rule until it gets back to the initial condition. And then we take a small step, and then it's just the same thing all over again, the full forward nonlinear pass. So the way we would do this in the old days is we'd be limited to a short period of time where we'd have to run a tangent linear model, and we do the same thing with the adjoint of the tangent linear model. But we were limited because that step, that back and forth, we would do maybe 5 or 10 of those, and then on an outer loop, do the fully nonlinear pass, which is very expensive. So we no longer need to do that, and we no longer need to have the adjoint code of the model. That's all happened automatically by using JAX. It's really an amazing technology. So, Mike, does that get to your question?
It does, but it kind of sounds really expensive still. And it's not, I
Yeah,
guess,
in
compared
fact,
to.
I've been working on this, yeah, for over a year, and it wasn't until I got my Grace Blackwell 10, my Spark, NVIDIA Spark, that has 128 gigabytes of combined high-speed memory for the GPU that I was able to hold the whole thing in memory and do this calculation.
Wow. Thank you.
You're welcome.
Thanks, Mike. Do we have any other questions? You can raise your hand or you can just type it in the chat. Yeah, go ahead, Adrian.
Can you hear me?
Yes.
I can.
Yes, Greg, great talk. I'm Adrian. So I work a little bit with GPU. So my question was going to be about mainly hardware. So just confess to me that you are using DGX Spark, and I also recently bought a DGX. I mean, and you said that with the 128 gigs, you were able to store everything on the hardware. Could you expand a little bit about the process of getting everything installed? Because I know NVIDIA puts all the tools out there, but were you really able to like load everything on GPU and run it with JAX?
Yeah, so thanks for the question, Adrian. So I had been running this on A100s and H100s, which have 80 gigabytes of memory, and I was always running out, no matter how finely I checkpointed. So it was exceeding the limits of my skills. And it wasn't until I got the Spark that I realized I could measure. It takes at least 94 with this model to take one step. So if you're familiar with the JAX technology, lax.scan and the .grad, I have some specialized routines that actually go through and manage that. And it's surprisingly efficient. So I've done these optimizations out to 10,000 epochs, and it takes about for these 48-hour forecasts through 1,000 epochs, takes about 3 hours on that Spark. So these are doable calculations once you can get enough of it in memory and do this checkpointing routine.
Thanks. He did a thumbs up, so I think that sufficiently answers it. James, I think you're next.
Hey, Jimmy.
Cool. Hi. Hey, Greg. Thanks. I had a question about the first half of the talk because we think of ERA5 as being like observations, and then you're changing it. So are the changes you're making going away from reality?
So I'm going to have to reshare my screen again to answer your question because I do have that in my backup slides. So can you see my slides?
Yeah, it's back on.
Yeah, so if you average over the whole year, this gives you a taste of what, on average, these corrections to ERA5 are doing. So the 850 hectopascal temperatures in the upper left show it's warming along the ITCC and it's cooling over the subtropical stratocumulus cloud decks. In the water vapor field at 700 hectopascals, it's moistening along the ITCZ and it's drying above those cloud decks. And then in the vertical motion field, it's increasing ascent in the ITCZ and increasing descent. So these are all indications of a multivariate, coherent correction on average that's increasing the intensity of the Hadley circulation in ERA5. And that's a known deficiency. When I first showed this at ECMWF, the folks who are working on ERA5 and ERA6, they know this and they were kind of happy to see it.
Interesting. All right. Thanks a lot.
Yeah, you're welcome.
Thanks. Next, we have Daryl.
Hey, Daryl.
Hey, Greg, great talk. I'm also going to ask about the first part in part. Thanks for giving us some confidence. We still have some job security and a lot of work to do on the DA side, and that we have more to squeeze out of the system. Although I'm wondering if you can preview some of your thoughts you alluded to about model error and whether or not some of your findings may be, I don't know how to untangle the model error part of it, and sort of you can get better answers, not necessarily for the right reason. Although I think you have some clues that what's happening in the initial condition is a real signal for which we can improve the initial conditions, but wondering how generalizable and how to think about the model error part of it and not correcting things in the wrong way for a better outcome.
You're exactly right, Daryl. And this is the age-old problem, right? Forever, we've had this ambiguity between initial condition error and model error, and they're all kind of mixed together. And it's pretty clear, so work that I'm writing up right now can replicate what we're seeing with GraphCast, both in neural GCM and with idealized Lorenz models. So we can do the perfect model experiments. We can also make them imperfect in controllable ways, and we get the same behavior. We get this exponential growth, and this looks like it's basically the growth of model error over time, and the optimal initial conditions are accommodating that. So that's, in a sense, that's bogus, right? In response to Jimmy's question, there does seem to be, on average, something that's physically sensible, but day in and day out, there's a lot of these corrections. Like a ballpark estimate would be at least half of it is probably encoding model error into those initial conditions. And I do think that the heat wave case was probably a bit of an outlier in that respect. The fact that we got such consistent adjustments in Pangu weather, we did not see that when we did all the Pangu weather forecasts for the entire year of 2020, the 732 samples. In terms of what to do about it, I'm super excited because I think we have the best opportunities. There are all kinds of ideas now, as you know, for new ways to do data assimilation in the latent space and purely from observations. I'm a bit of an old school guy, and I think there's a lot of opportunities here for really long window weak constrained 4D-VAR, which is what we're actively pursuing right now. And that's about all I can say without giving away the details. Does that help?
Yeah, thanks. I'm also excited. It's just when we thought we had it all figured out and we knew what we're going to be doing for 10 years, this comes along, and now it's wide open. We're doing so many different things that I never thought would even be possible, what we'd be thinking about. So I think it's a real
It's a super,
opportunity to move
super
the needle
exciting
on
time.
stuff we thought was impossible to solve. So it's really exciting time.
Exactly. Yeah. I've never been this excited in my entire career. Thanks, Daryl.
Thanks. So next is Kenya.
Hey, Kenya.
Okay. I have a question on the second part. First of all, think it was very interesting, and I think there's a lot of application we can do. So thanks for sharing that research. So my question is, have you thought about like changing the target intensity? So right now, I think you're setting the specific value. But I think there you could possibly like investigate black swans, not gray swans, and then like just keep lowering the threshold and see if if there will be any the lower limit that we could get something. Have you
I
thought of
agree.
it?
And in fact, when I go out to 10,000 epochs, I only showed you 1,000. The pressure goes below 900 hectopascals. It does seem to be reaching a limit at that point. You might wonder, even though this is a more or less a traditional physics model, how realizable this is. And I can just tease that one of my students has put this initial condition into MPass and run it at coarse resolution in MPass. And it doesn't get as deep, but it's still a surprisingly similar forecast. So yeah, this is just the first step in this direction. And I think you're right. We could explore true black swans, things that are way outside of the observational record. And I've presented this other places, and folks are very excited about this for extreme precipitation events, which is on
I
everybody's
was
mind.
thinking
Yeah.
about application to like
Yeah.
probable maximum precipitation and stuff. So
Yeah, exactly.
thank you.
Thank you, Kenya.
Thank you. And now Louis.
So, Greg, I had to jump in after you said you've never been so excited before. So when I saw you,
It's the second time.
Yeah, second time. Okay. Listen, you picked Sandy as far as I could gather, as this gray swan. If you're looking for another one, try Hakim in 2015. That sank what was the name of the ship? The El Fargo. Yeah, El Fargo. It cost 33 lives between the Bahamas and the United States. But a captain bet that it was going to actually take off to the northeast, and the storm drifted to the southwest and crushed them. Like Sandy, it has a singular point in the flow field, and literally if you're 1 or 2 grid points to the east of that, it would go to the northeast. If you're 1 grid point to the west of it, you were going southwest. And it was really one of the more tragic things I was witnessing in real time. So, and a very difficult, track forecast to boot. So it'd be interesting to see if the kinds of results you're getting with this gray swan would be similar to another gray swan, which has similarities, but much more involved with a much more tighter deformation field with a singular point in it. And it was horrible to see what was happening in real time. I can witness that one. So anyway, I just thought I would bring that up and then wonder, whether you'd get the same kind of sensitivity that you're seeing here with respect to the Sandy challenge.
Thanks, Louis. I'll take a look at that case. I would say that another caveat on what I've shown you here is that the model that I used for this optimization was very coarse. So if the small scale details matter, it may not be resolvable with the resolution of the model that I'm using. And that gets back to these resource issues that I talked about earlier. I've run a slightly higher resolution version of the model, but if it's really small scale details that matter, it may be on the reach of what the tool that I'm using right now.
It was a large scale deformation field.
Oh, I see. Yeah.
But a very, very definitive singular point in that field. but southwest and northeast. And that was the track forecast challenge of that storm.
So Maria was a bit like that. Maria went to the north and it had this stall point, and it looked like it could have gone either way, and it wound up slowly moving off and then accelerating to the east. And so, that one required whatever the special nudge was to the initial conditions. When it got to that point, it did the turn to the left and interacted with a mid-latitude trough. That always seems to be the essential thing.
And with Sandy, actually, from 5 days out, the European was putting it straight up the coast, and the GFS was going out.
Yeah. Right.
And there were ensembles that were showing it coming back. So actually, it did go to the east of a deformation point, a singular point. But that ridge really played its role later in the track aspect of that. It literally stopped it further north and then accelerated it to the west. So I think you got a twofer here with respect to Sandy. But Joaquin was just a well-behaved deformation field, but a very strong singular influence from that singular point. I just wanted to point that out. So maybe using those two cases will give you some kind of range of solutions that you might be seeing with this technique.
Cool. Thank you, Louis.
And of course, good seeing you again.
You too.
Do we have any more questions? We got like 2 more minutes, probably time for one more question if anybody has anything. Yeah, go ahead, Adrian.
Sorry, just to ask Greg, have you explored the Earth 2 Studio module from NVIDIA where they have the huge ensembles receipt and, technique?
I know of it, but I have not used it myself.
Because when I was like hearing the first part, especially of your talk, that reminded me of like kind of like those type of techniques that I haven't explored. I want to use it for heat wave forecasting beyond week 2 and subseasonal to subseasonal. But I haven't done it, so I didn't know if you had, in case because memory load is a concern at this point, right? With models, also the number of ensembles you do. So I have managed a few days of forecasting with their receipts on the website, but I didn't know if you have played with that.
Yeah, I haven't used any of these frameworks really. I'm familiar with them. I used some of the ones in the early days, but for me, I like to have my hands as close to the bare metal, so to speak, as possible, because these calculations require care in memory management. And I'm writing the JAX directives and the decorators myself. This is all hand coded. This was kind of even before the LLMs became capable with these sorts of things. So the large ensemble part is relatively straightforward. These models are so fast and it parallelizes trivially that you can make them as big as you like. S2S is a great idea. I've already done a few tentative explorations there with optimizing the sea surface temperature and going out really far. And I think there's a lot of potential there. That's about what I can say at this point. Thanks, Adrian.
A quick one. How do we know that the AI models are not hallucinating these extreme events?
Yeah, we don't, which is the main reason why I use Neural GCM. So the Neural GCM has a traditional dynamical core, so it's integrating vorticity, divergence, thermodynamic energy equation, continuity equations for water vapor, cloud ice, cloud water in a conventional spherical harmonic solver. And then every so often, there's another step where it calls a learned model with those inputs to get essentially everything else that's mixed, most stuff that's related to clouds and whatnot, but also numerical errors and whatever it takes to correct the solver, the traditional solver, to make a better forecast. But when JAX is tracing through, it's spending a lot of time going through the dynamical core, the traditional primitive equation solver that is kind of at the heart of all traditional NWP models.
So it's tied to physics. Okay, thanks.
It's tied to physics, but again, to be sure, like I was saying earlier, I have a grad student who's running these initial conditions, these gray swan initial conditions, in a truly kind of state-of-the-art operational model. MPAS is the best model we have right now. Is going to become the operational model at NOAA for weather forecasting. Traditional model with all the traditional parameterization schemes, so all of the microphysics and boundary layer schemes and whatnot. So that's a really hard test, Mike. That's taking this initial condition and putting it into a flagship operational style model.
Cool. Thanks. Thanks so much.
You're welcome.
So we are at time. So thank you everybody for attending this talk and asking great questions. And big thanks to Greg for giving us this great talk.
Thanks, everybody.
Yeah, so have a great afternoon. We will be back with our seminars next week. Thank you.
See you, everybody.